Welcome to the video on direct versus inverse variation. To distinguish between direct variation and inverse variation, let's just write down what's happening. In direct variation, as x increases, y is also going to increase. So with direct variation, think of x and y both doing the same thing. They both increase. Inverse variation, as x increases, y will do the opposite. It will decrease. So as we write an equation for something that varies directly, we are going to set up the equation as y equals a constant times x, right? So think about it. If you put in a bigger number for x and it gets multiplied by a constant, y is going to be bigger, right? As x goes up, y goes up. But with inverse variation, we actually are going to have y equals k divided by the x. So the bigger you make the denominator of a fraction, the smaller the answer is. And that's what's happening with inverse variation. So let's try some problems. Example 1, y varies directly with x. So as soon as we see varies directly, we know that we're going to use this setup here. So let me write that down. Find the equation to model the situation when x is 5 and y is 20. So they're giving us an x and a y value. That way we can find what k is. So let's plug in 20 for the y. We don't know k, and x is 5. So let's solve for k. Divide both sides by 5. So k equals 4. So we now have to write our equation with what k actually is. Y equals 4x. Now hopefully that equation looks pretty familiar. You've been working with these types of equations probably since pre-algebra. That's going to be the equation of a line. So you've been working with direct variation for many units now. What you have not been working with is inverse variation. So let's try one of those. In example 2, y varies inversely with x. So let's set this one up as y equals k over x. And this time we're finding the equation to model a situation when x is 7 and y is 2. So we're going to plug in 2 for y, leave k as k because we don't know what it is, and 7 for x. Now how would you solve for k here? We need to undo what's happening to it. Well, we're dividing by 7. So to undo that, we would multiply both sides by 7. So we would get k is 14. So this equation is y equals 14 over x. So this is the first time that we've had some equations that actually have x in the denominator here. Wouldn't that also be x to the -1, right, since it's in the bottom of the fraction? And that's why we have a whole new unit to deal with these things called rational functions. So when in real life would you ever have this type of example? Because you've done lots of word problems that have linear equations. That's the direct variation, right? I want you to write down an example right here in this spot. Okay, let's use really paying attention. For full credit on homework, I want you to write down an example of what would give you an equation y equals 4 times x. So think of a real life example of something that varies directly. So think of it as x goes up. What is x going to represent? How would y go up? What would that represent? Okay. I'm going to give you an example of an inverse variation on example 3. At a cheesecake factory, the management has a special company party every year at Six Flags. For a set fee of $8,000, the company employees can have the entire park to themselves for a day. So it doesn't matter how many people they bring, they have to pay $8,000. If the employees split the cost, write an equation which we're going to call C of x, which stands for the cost per employee, for X employees going. So X is going to represent the number of employees that go. C of X is going to be the cost per employee. So I guess this isn't so nice that the management has a special party for them because they still have to pay to go, but at least they get the chance to do this. So let's think about this. I'm going to make a table. X is the number of employees, and C of X is the cost per employee. So let's say that no employees worked for the company. That would make absolutely no sense. There wouldn't be a cost. Not that the cost is zero, it's just that this situation wouldn't happen. It would be undefined. What if there were 20 employees? To do that, wouldn't we do 8,000 divided by how many employees, right? 20, which would be 400. So each employee would owe $400. What if there were 40 employees? Wouldn't we do 8,000 divided by 40? And that would be $200. I sure hope there's more than 40 employees. That's an expensive ticket, right? I'd rather just go to Six Flags on my own. What if there were 80 employees? Let's do 8,000 divided by 80. That's 100. Okay, looking better. Let's do 100 employees. What was 8,000 divided by 100 going to get you? 80. Okay. Let's really jump it up here. Let's go to 200. What if there were 200 employees? 8,000 divided by 200. That's more like it. $40, yes. And then what if there were X employees? Look at the pattern. Look at what's happening. We keep taking the 8,000 and we're dividing by a different number each time. In fact, look what we're dividing by. We're dividing by X. So I say that this is 8,000 divided by X. That's what the equation is going to be. C of X equals 8,000 over X. Right? That's inverse variation, a constant divided by X. As the number of employees goes up, the cost per employee goes down. That's inverse variation. So now let's just graph this. What do we do at 0? We're going to have to think about that. We can get the 20, 400. Oh, that doesn't fit on here. Let's try 40 employees. That will cost 200 per person. 80 employees will cost 100 per person. 100 employees will cost 80. 200 employees will cost 40. Look what's happening here. We definitely have a curve decreasing, right? As X is increasing, Y is decreasing. And we said that 0 doesn't have a value here. Would the cost per employee ever be $0? No, right? They'd have to pay something. So we know that this graph is never going to hit 0. But we also know that it's not going to have a y-intercept. And that's why we're going to get a vertical asymptote and a horizontal asymptote. And the curve's going to fit. Oh, this is hard for me to do on the computer. I'm trying. Our curve's going to fit right in between those. And that's what inverse variation looks like. Let's do one more quick example. Sullivan Stadium can be rented out for a set price. So kind of like the Six Flags problem we just did. Except we don't know the price. A soccer team of 14 members decides to rent out the stadium for a day, and they each need to pay $50. All right, well, let's just figure out how much does the stadium cost. How would we do that? If they each are paying $50, we don't know the cost. That's like our constant, and there were 14 people. How would we find K? Oh, we'd multiply both sides by 14, right? You might just say that in the beginning. It's 14 times 50. And what is 14 times 50? I am typing that in. I get 700. So this is the cost of the stadium. That's the constant. It's not going to change. So the equation is y equals 700 over x. And x is going to represent the number of people who are on the team. Now the question says, how much would they need to pay if 16 members were on the team? Well, that's easy. Let's take the $700 for the stadium and divide it by 16. Type that in and I get $43.75. So there's a real life example, again, of how inverse variation is really all over the place. Now it's time for you to try some practice. Good luck.